Thermal conductivity 149W/MK. Electrical assistivity 2.3103 M at 20 degrees Celsius. 4. Modern world economy. The small portion of very highly purified elemental silicon used in semiconductor electronics, and LT 10%, is essential to transistors and integrated circuit chips used in most modern technology such as smartphones and other computers. In 2019, 32.4% of the semiconductor market segment was for networks and communications devices, and the semiconductors industry is projected to reach $726.73 billion by 2027. 10. Silicon is an essential element in biology. Only traces are required by most animals, but some sea sponges and microorganisms, such as diatoms and radiolaria, secrete skeletal structures made of silica. Silica is deposited in many plant tissues. 11. Contents. History. Discovery. Silicon semiconductors. Silicon age. Characteristics. Physical and atomic. Electrical. Crystal structure. Isotopes. Chemistry and compounds. Silicides. Silans. Halides. Silica. Silicic acids. Silicate minerals. Other inorganic compounds. Organosilicon compounds. Silicone polymers. Occurrence. Production. Applications. Compounds. Alloys. Electronics. Quantum dots. Band gap 1.12 eV at 300 K. Magnetic ordering. Demagnetic. 5. Molar magnetic susceptibility 3.9106 cm 3/mol. 298 K. 6. Young's modulus 130-188 GPa. 7. Shear modulus 50-180 GPa. 7. Bulk modulus 97.6 GPa. 7. Poisson ratio 0.0640.28. 7. Mohs hardness 6.5. Cas number 7440-21-3. History. Naming after Latin silex or silicis meaning flint. Prediction. Antoine Lavoisier, 1787. Discovery and first isolation. Jöns Jacob Bertillon, 1823, named by Thomas Thomson, 1817. Main isotopes of silicon. Isotope abundance. Half-life, T1/2. Decay mode. Product 28 cyanine 2.2% stable, 29 Cy 4.7% stable, 30 Cy 3.1% stable, 31 Citrase 2.62H, 31 P32 Citrase 153Y, 32P. Biological role. Marine microbial influences. Human nutrition. Safety. See also. References. Bibliography. External links. External links. History. Owing to the abundance of silicon in the Earth's crust, natural silicon-based materials have been used for thousands of years. Silicon rock crystals were familiar to various ancient civilizations, such as the predynastic Egyptians who used it for beads and small vases, as well as the ancient Chinese. Glass containing silica was manufactured by the Egyptians since at least 1500 BC, as well as by the ancient Phoenicians. Natural silicate compounds were also used in various types of mortar for construction of early human dwellings. 12. Discovery. Jöns Jacob Bertillon discovered the silicon element in 1823. In 1787, Antoine Lavoisier suspected that silica might be an oxide of a fundamental chemical element. 13. But the chemical affinity of silicon for oxygen is high enough that he had no means to reduce the oxide and isolate the element. 14. After an attempt to isolate silicon in 1808, Sir Humphrey Davy proposed the name silicium for silicon, from the Latin silex, silicis for flint, and adding the ium ending because he believed it to be Amator. 15. Most other languages use transliterated forms of Davy's name, sometimes adapted to local phonology, for example German Silesium, Turkish Silesium, Catalan Silici. A few others use instead a calque of the Latin root, for example Russian, from flint, Greek from fire, Finnish pi from pikivi flint, Czech kemp from kimen quartz, flint. 16. Gay-Lussac and Thenard are thought to have prepared impure amorphous silicon in 1811, through the heating of recently isolated potassium metal with silicon tetrafluoride, but they did not purify and characterize the product, nor identify it as a new element. 17. Silicon was given its present name in 1817 by Scottish chemist Thomas Thomson. He retained part of Davy's name but added on because he believed silicon was a non-metal similar to boron and carbon. 18. In 1824, Johns Jacob Bertillaius prepared amorphous silicon using approximately the same method as Gay-Lussac, reducing potassium fluorosilicate with molten potassium metal, but purifying the product to a brown powder by repeatedly washing it. 19. As a result, he is usually given credit for the element's discovery. 20. 21. The same year, Bertillaius became first to prepare silicon tetrachloride. Silicon tetrafluoride had already been prepared long before in 1771 by Carl Wilhelm Scheele by dissolving silica in hydrofluoric acid. 14. Silicon in its more common crystalline form was not prepared until 31 years later, by Devil. 22. 23. By electrolyzing a mixture of sodium chloride and aluminium chloride containing approximately 10% silicon, he was able to obtain a slightly impure allotrope of silicon in 1854. 24. Later, more cost-effective methods have been developed to isolate several allotrope forms, the most recent being silicene in 2010. 25. 26. Meanwhile, research on the chemistry of silicon continued. Friedrich Wöhler discovered the first volatile hydrides of silicon, synthesizing trichlorosilane in 1857 and silane itself in 1858. But a detailed investigation of the silanes was only carried out in the early 20th century by Alfred Stock, despite early speculation on matter dating as far back as the beginnings of synthetic organic chemistry in the 1830s. 27. 28. Similarly, the first organosilicon compound, tetraethylsilane, was synthesized by Charles Friedel and James Crafts in 1863, but detailed characterization of organosilicon chemistry was only done in the early 20th century by Frederick Kipping. 14. Starting in the 1920s, the work of William Lawrence Bragg on X-ray crystallography successfully elucidated the compositions of the silicates, which had previously been known from analytical chemistry but had not yet been understood, together with Linus Pauling's development of crystal chemistry and Victor Goldschmidt's development of geochemistry. The middle of the 20th century saw the development of chemistry and industrial use of silocanes and the growing use of silicone polymers, elastomers, and resins. In the late 20th century, the complexity of the crystal chemistry of silicides was mapped, along with the solid-state physics of doped semiconductors. 14. Silicon semiconductors. The first semiconductor devices did not use silicon, but used galena, including German physicist Ferdinand Braun's crystal detector in 1874 and Indian physicist Jagadish Chandra Bose's radio crystal detector in 1901. 29. 30. The first silicon semiconductor device was a silicon radio crystal detector, developed by American engineer Greenleaf Whittier Picard in 1906. 30. In 1940, Russell O discovered the p-n junction and photovoltaic effects in silicon. In 1941, techniques for producing high-purity germanium and silicon crystals were developed for radar microwave detector crystals during World War II. 29. In 1947, physicist William Shockley theorized a field effect amplifier made from germanium and silicon, but he failed to build a working device, before eventually working with germanium instead. The first working transistor was a point-contact transistor built by John Bardeen and Walter Brattain later that year while working under Shockley. 31. In 1954, physical chemist Maurice Tannenbaum fabricated the first silicon junction transistor at Bell Labs. 32. In 1955, Carl Frosk and Lincoln Derrick at Bell Labs accidentally discovered that silicon dioxide, SiO2, could be grown on silicon. 33. Anthe later proposed this could mask silicon surfaces during diffusion processes in 1958. 34. Silicon Age. The Silicon Age refers to the late 20th century to early 21st century. 35, 36, 37. This is due to silicon being the dominant material of the Silicon Age, also known as the Digital Age or Information Age, similar to how the Stone Age, Bronze Age and Iron Age were defined by the dominant materials during their. The MOSFET, also known as the MOS transistor, is the key component of the Silicon Age. It was invented by Mohammed M. Attallah and Dewan Kang at Bell Labs in 1959. Respective ages of civilization. 35. Because silicon is an important element in high-technology semiconductor devices, many places in the world bear its name. For example, Santa Clara Valley in California acquired the nickname Silicon Valley, as the element is the base material in the semiconductor industry there. Since then, many other places have been dubbed similarly, including Silicon Wadi in Israel, Silicon Forest in Oregon, Silicon Hills in Austin, Texas, Silicon Slopes in Salt Lake City, Utah, Silicon Saxony in Germany, Silicon Valley in India, Silicon Border in Mexicali, Mexico, Silicon Fen in Cambridge, England, Silicon Roundabout in London, Silicon Glen in Scotland, Silicon Gorge in Bristol, England, Silicon Alley in New York, and Silicon Beach in Los Angeles, California. 38. Characteristics. Physical and atomic. Silicon crystallizes in adamant cubic crystal structure by forming sp3 hybrid orbitals. 39. A silicon atom has 14 electrons. In the ground state, they are arranged in the electron configuration, Ne, 3s23p2. Of these, 4 are valence electrons, occupying the 3s orbital and 2 of the 3p orbitals. Like the other members of its group, the lighter carbon and the heavier germanium, tin, and lead, it has the same number of valence electrons as valence orbitals, hence, it can complete its octet and obtain the stable noble gas configuration of argon by forming sp3 hybrid orbitals, forming tetrahedral 6-4 derivatives where the central silicon atom shares an electron pair with each of the 4 atoms it is bonded to. 40. The first 4 ionization energies of silicon are 786.3, 1576.5, 3228.3, and 4354.4 kJ/mol respectively. These figures are high enough to preclude the possibility of simple cationic chemistry for the element. Following periodic trends, its single bond covalent radius of 117.6 pm is intermediate between those of carbon, 77.2 pm, and germanium, 122.3 pm. The hexacoordinate ionic radius of silicon may be considered to be 40 pm, although this must be taken as a purely notional figure given the lack of a simple Psi4+ cation in reality. 41. Electrical. At standard temperature and pressure, silicon is a shiny semiconductor with a bluish-gray metallic luster, as typical for semiconductors. Its resistivity drops as temperature rises. This arises because silicon has a small energy gap, band gap, between its highest occupied energy levels, the valence band, and the lowest unoccupied ones, the conduction band. The Fermi level is about halfway between the valence and conduction bands and is the energy at which a state is as likely to be occupied by an electron as not. Hence a pure silicon is effectively an insulator at room temperature. However, doping silicon with a pnictogen such as phosphorus, arsenic, or antimony introduces one extra electron per dopant, and these may then be excited into the conduction band either thermally or photolytically, creating an N-type semiconductor. Similarly, doping silicon with a group 13 element such as boron, aluminium, or gallium results in the introduction of acceptor levels that trap electrons that may be excited from the filled valence band, creating a p-type semiconductor. 42. Joining N-type silicon to p-type silicon creates a p-n junction with a common Fermi level. Electrons flow from N to p, while holes flow from p to N, creating a voltage drop. This p-n junction thus acts as a diode that can rectify alternating current that allows current to pass more easily one way than the other. A transistor is an n-p-n junction, with a thin layer of weakly p-type silicon between two n-type regions. Biasing the emitter through a small forward voltage and the collector through a large reverse voltage allows the transistor to act as a triode amplifier. 42. Crystal structure. Silicon crystallizes in a giant covalent structure at standard conditions, specifically in a diamond cubic lattice, space group 227. It thus has a high melting point of 1414 degrees Celsius, as a lot of energy is required to break here strong covalent bonds and melt the solid. Upon melting, silicon contracts as the long-range tetrahedral network of bonds breaks up and the voids in that network are filled in, similar to water ice when hydrogen bonds are broken upon melting. It does not have any thermodynamically stable allotropes at standard pressure, but several other crystal structures are known at higher pressures. The general trend is one of increasing coordination number with pressure, culminating in a hexagonal close-packed allotrope at about 40 gigapascals known as Psi7, the standard modification being Psi-I. An allotrope called BC8, or BC8, having a body-centered cubic lattice with 8 atoms per primitive unit cell, space group 206, can be created at high pressure and remains metastable at low pressure. Its properties have been studied in detail. 43. Silicon boils at 3265 degrees Celsius. This, while high, is still lower than the temperature at which its lighter congener carbon sublimes, 3642 degrees Celsius, and silicon similarly has a lower heat of vaporization than carbon, consistent with the fact that the Psi-Psi bond is weaker than the C-C bond. 42. It is also possible to construct silicene layers analogous to graphene. 25. 26. Isotopes. Naturally occurring silicon is composed of 3 stable isotopes: 28 Psi, 92.23%, 29 Psi, 4.67%, and 30 Psi, 3.10%. 44. Out of these, only 29 Psi is of use in NMR and EPR spectroscopy. 45. As it is the only one with a nuclear spin, I equals 12. 27. All 3 are produced in type Ia supernovae. 46. 47. Through the oxygen burning process, with 28 Psi being made as part of the alpha process and hence the most abundant. The fusion of 28 Psi with alpha particles by photodisintegration rearrangement in stars is known as the silicon burning process, It is the last stage of stellar nucleosynthesis before the rapid collapse and violent explosion of the star in question in a Type II supernova. 4820 radioisotopes have been characterized, the two stablest being 32 Psi with a half-life of about